Alright gang, here we go. This is for Chem 1, Unit 12, Part 7. We're going to talk about pH scale, a little wrap up of our unit on acids and bases. We've kind of danced around this topic, kind of all unit, just kind of keeping up with the idea of like, well, what is an acid? What is a base, right? And so something that is acidic, okay, is some, we've had three different definitions for defining acidity, but what we really need is a way to keep track of it quantitatively, be able to express these numbers or these acidity and basicity by relating the numbers to one another. And so that's where we get this idea of pH and pOH. All right. Now, whenever you see in science or math this p value, like a p in front of some variable, what this really means is that you're taking the negative log of whatever that variable is. So in this case, it's the negative log of our h, all right? And then in this case, it's the, it's the negative log of your OH. Okay, that's all that means right here. So when we're talking about pH, this is what we're going to focus on first. All we're taking is our negative log of our H plus. And remember, H plus is really hydronium, because H plus, these little protons don't exist by themselves. They get stabilized by our water molecule, form hydronium. So to find the pH, you just take whatever your concentration of your hydronium is and take the negative log of it. You hit the negative button, you hit the log button, you type in your concentration, you're done. And that's your pH value for your solution. Now, remember, because this is base 10, in order to cancel out that, you have to take it to 10 to the whatever it is. So if you want to calculate your hydronium, so say you're given here, you would be given your calculate your hydronium concentration. You want to find pH. If you were in the flipped situation where you were given pH and you needed to find hydronium, you would simply do it like this. You just hit 10 in your calculator, the caret button, and then hit negative and whatever your pH value is. All right, and that would give you your concentration of your hydronium. All right, so remember, pure water has a concentration of hydronium. In pure water, your concentration of hydronium is equal to, and we talked about this in the last video, is equal to 1.00 times 10 to the minus 7th, right? That's the autoionization of water. So the negative log of this value, the 1's cancel, the 7 comes out front, and the negatives cancel, and so you just get 7, all right? And so in that pure water value, your pH and your pOH are equal to each other, and you have a neutral solution. All right, and so this is defined as neutral. And so that's where we get pH of 7 is neutral, is because in pure water, we've defined that as neutral pH. All right, or a neutral solution. So if your pH is less than 7, you're acidic. That means you have a greater concentration. And if your pH is greater than 7, you have a basic solution. The lower the pH is, the more acidic the solution, and the higher, the more basic the solution. And so really this is where we get that quantitative ability to be able to look at a value, that pH, and be like, you are more acidic than that one. You are more basic than the other, so on and so forth. Now, one thing to keep track of is your pH units, okay, because it's a logarithmic. Your pH corresponds to a factor of 10 difference in acidity. So if your pH goes up by 1, that means it's 10 times more acidic. For example, if you go from a pH of 1 to a pH of 2, then you have lost, you're 10 times less acidic by increasing from 1 to 2. So 1 is 10 times more acidic than 2. All right. So here's just some pH values here. So remember, 7 is our neutral guy. So freshly distilled water, saliva, milk has lactic acid, so it's slightly acidic. Pure rain is actually slightly acidic because of carbon dioxide that's dissolved in it. Coffee, your sulfuric acid, battery acid up here, this is very, very acidic. Your stomach acid is about at 1. And then on the other side, these are some other things we've looked at. Household bleach is basic. It's about at like a 12.5. Your ammonia, 11 and change, milk and magnesia, 10 and change, so on and so forth. Okay, so these are some common pH values here. All right, and remember, so this is kind of an important little table here. Okay, remember our pH values here. Again, neutral, and then going up is acidic, going down is basic, and we've got our times acidity or alkalinity. All right, so this is just how basic it is of pure water. So this is 10 times more acidic than pure water. The pH of 5 is 100 times more acidic. Notice that we're just adding 1 0 each time because we're just increasing by 10-fold. All right, same thing with our basicity. This is 10 times more basic than neutral water. water, pH of 8. pH of 9 is 100 times more basic, okay, so on and so forth. All right, this is just another way of looking at your acidic scale. Usually we use reds to represent our acids and blues to represent our bases. Okay, so let's do a couple practice problems here. It says, what is the pH of a 3.5 times 10 to the minus 6 molar HCl solution? So remember, our pH is equal to the negative log of the concentration, so that's 3.5 times 10 to the minus 6th. All right, so we pick up our calculator. We say negative log 3.5 e to the minus 6th. All right, end parentheses, hit the button, okay? And then one thing you have to keep track of here is your sig figs. When we calculate sig figs for pHs, your sig figs is always doesn't count until after the decimal place. So your calculator here spits out this number 4.5559. All right, 5.4559. 5.4559. So this is what our calculator spits out. Now we have to think about our sig figs. This value here has 2 sig figs because that's what's in our coefficient. So we need to round it to 2. So you might, in the past, you'd say, oh, it's 5.5, right? Well, that's not quite right. Because pH is logarithmic, the number before the decimal is a placeholder. So that placeholder value doesn't have sig figs. So your sig figs actually start here. These two are your significant digits. This is a placeholder. This tells you how many this is. Okay, and so what this becomes really is 5.46. So that's the correct number of sig figs to calculate our pH. All right, so that's the pH of this solution. So if we had 3.5 times 10 to the 6 molar HCl, it would be at a pH of 5.46. All right. Now this guy, it says calculate what is the pH of 7.0 times 10 to the minus 6 molar HCl. Well, if we take this guy then, all right, now you might be noticing, you chemists that are paying attention here, you notice, oh, this is double, so maybe my pH should double. Well, that doesn't make sense, right? Because, our pH, this concentration has gone up, so our pH should go down, right? It should be more acidic, so maybe it'll go down by half. All right, well, let's try it out. So it would be negative log of 7.0 times 10 to the minus 6th. All right, so we should test that out. We say negative log of 7 e to the minus 6th. All right, and we get 5.15. All right, again, 2 sig figs, right? So 5.15. All right, so that's not half of what that is. That's only slightly more acidic. Remember, when you double, even though this is doubled, okay, our pH, one whole value change of pH is equal to 10 times more acidic. This is not 10 times more acidic. It's only twice the concentration. Okay, so it's the pH only goes down by this much. All right, and now it says what is the H plus solution, the hydronium concentration of a solution that has a pH of 4. So remember the other formula we learned today, the concentration of our hydronium, okay, is equal to 10 to the negative pH. All right, so we'll write that in, 10 to the negative pH. So it'd be 10 to the negative 4. All right, so you could punch that into your calculator, and unsurprisingly, you'd get 1 times 10 to the minus 4th. All right. All right, so that's pH. pOH is the same idea as pH, but slightly different. Okay, pOH is the negative log of the concentration of hydroxide. The pOH of pure water is still equal to 7, all right, just like the pH defined as neutral. Now, this is backwards, so you got to pay attention. If your pOH is less than 7, that means you're basic. Okay, and remember with your pH, if it was less than 7, it was acidic. This is the exact opposite. Don't let this throw you off. Okay, your pOH, all right, tells you how basic you are, and your pH tells you how acidic you are. So if you have a pOH of 13, that means you're actually pretty acidic. Okay, so let's do this. All right, it says what is the pOH, okay, of a 3.5 times 10 to the minus 6 molar NaOH solution. Okay, so pOH is equal to the negative log of the concentration of hydroxide. Well, this is a strong base, so all of that's going to turn into hydroxide, so this becomes 3.5 times 10 to the minus 6. All right, and this will be the same number as we got in this previous practice problem over here. So we'll just get 5.46 again, because it's the exact same thing. 5.46. So that's the pOH of our solution. It's a slightly basic solution. Okay, all right, and this says what is the pOH of a 3.5 times 10 to the minus 6 molar HCl solution? But be careful here. This, okay, is actually the same as the concentration of H+. So we have to use our formula from before. So remember our autoionization formula, we said that the concentration of hydronium, okay, times the concentration of hydroxide is equal to Kw. So our pOH, okay, our pOH is equal to the negative log of the concentration of the hydroxide. All right. Okay, but we don't have hydroxide. We have our H plus solution. So we got to solve for our hydroxide first. So our concentration of our hydroxide would be equal to Kw divided by our hydronium concentration. All right, so Kw is 1 times 10 to the minus 14th. And our H plus is 3.5 times 10 to the minus 6th. All right, so we take 1 e to the minus 14th divided by 3.5 e to the minus 6th, and we get 2.857 times 10 to the minus 9th. Now, you might be tempted to round that off for sig figs, but that's not our final answer, so we don't want to round for sig figs yet. So 2.857 times 10 to the minus 9th. 2.857 times 10 to the minus 9th. All right, so that means our negative log is equal to the concentration of our hydroxide, 2.857 times 10 to the minus 9th. So that means our pOH is equal to, take the negative log of our answer, 8.54. How many sig figs? 2 sig figs, so it would be 8.54. All right. So that's our pOH of our solution. Okay. Now, a fun little trick here to save you some time, so you don't necessarily have to do that. Now we know we just established this with this is equal to our, this is what we learned when we talked about the autoionization of water, that the concentration of hydronium times the concentration of the hydroxide is equal to 1 times 10 to the minus 14th. Okay. Now, if you imagine you took the negative log of both sides, right? So you take the negative log of both sides, so this would be the negative log of the concentration of hydronium, okay, times the concentration of hydroxide. Okay, and then you take the negative log of this, 1.00 times 10 to the minus 14th. If you take the negative log of that, remember our log rules that said that if we have, like, remember this log rule, this was probably a long time ago in your algebra class, x times y. If you have the log of two things multiply to each other, that's the same thing as saying the log of x plus the log of y. Remember that? So we can, what we can do is we can say, well, that's the same thing as the negative log of the concentration of H3O plus the negative log of the concentration of hydroxide, right? And that's equal to the negative log of all this, 1.00 times 10 to the minus 14th. Now we can say, well, we know that the negative log of the concentration of hydronium, well, that's just equal to your pH. The negative log of the concentration of hydroxide, well, that's just equal to your pOH. All right, and then if you punch this into your calculator and that magical thing happens, the 1's go away because the log of 1, and then 14 comes down, so and it cancels with the positive, and you just end up with 14. So really what we get is that our pH plus our pOH will always equal 14. Isn't that nice? So nice. So then we get this little roadmap we can go from. So this is our concentration of hydronium. This is our concentration of hydroxide. And so what we can do is, using this setup here, is we can go from one corner to the next, or just across. So like, say I'm given the hydronium concentration and I want to find the pH, then I'm just going to go this way. So I just find my pH is equal to the negative log of H plus. So I'm just going to plug that in a negative log. Okay, or if I, this is pretty easy when you're going from one to the next, but sometimes it can get confusing when you got to go catty corner here. So your H plus, say if you wanted to find the pOH, okay, you have two options. You can go from your H plus down to your pH by using the negative log of the concentration of H plus, and then subtract that from 14 to go over to your pOH using this formula right here. Or you could go the opposite way. You could use your Kw, your 1 times 10 to the minus 14th, and divide that into that, and your Kw, and we'll get your concentration of hydroxide, and then take the negative log of that. And so really, from one place to the next, on any point on this map, you could go from one place to the next. So this is a good thing to have memorized, a good tool to have in your pocket. Make sure you get really comfortable with going from one corner to the next, one side to the next, so on and so forth. The nice thing is, as opposed to like our stoichiometry maps, is that no matter what we do, these guys will always only be 2 steps maximum. Okay, so combining the two formulas, we're going to do a couple of problems here. It says, what is the concentration of hydroxide in soil that has a pH of 4.5? So we're going from pH to the concentration of hydroxide. Okay, so let's look at our roadmap. So we're going from pH, this is where we're starting right here, we're going to the concentration of hydroxide. So we have two options, okay? We can find the concentration of hydronium and then go to the concentration of hydroxide, or we can go to the pOH and then go to the concentration of hydroxide. Well, since we haven't used this formula yet, let's go down and to the right. So we're going to go from our pH to pOH first. Now we know that pH plus your pOH is equal to 14. All right, so that means your pOH is equal to 14 minus your pH. All right, so our pH is 4.5, so it'd be 14 minus 4.5. Okay, and so that'd be 9.5. All right, so that's our pOH. All right, so now we're right here on our roadmap, 9.5. So now we're going to go up here. All right, so we're going to use this formula here. Our concentration of hydroxide is equal to 10 to the negative pOH. Kind of turned your head funny to see it, but that's all right. All right, so that means our concentration of hydroxide is equal to 10 to the negative pOH. So it would be 10 to the negative 9.5. All right, so we say 10 to the negative 9.5. We get 3.16 times 10 to the minus 9th. Now you have to think, or minus 10th. Okay, now this is another thing to keep track of here. This can get confusing, so 3.162. All right, it's thinking about sig fig. It's 162 times 10 to the minus 10th. So you got to think about your sig figs here. All right. So remember, when we talk about sig figs with pHs, the sig figs start with the decimal. This guy does not count as a significant figure. So this is where our sig fig starts, that value. So it has one significant figure. So that means this will round to this value right here. So essentially, this guy just becomes 3 times 10 to the minus 10th molar. All right. So that's the concentration of hydroxide at 4.5. Okay. Let's do another one. So now it says calculate the pH and the pOH of a solution that has a concentration of hydroxide of that. All right, so now we're going to go to two different things. So we're starting here, and we want to find concentration of pOH and the concentration of pH. All right, so that's pretty easy, right? So we can find the pOH easy enough because that's just equal to the negative log of the concentration of hydroxide. So that means that's just equal to the negative log of 1.0 times 10 to the minus third. Right? So this will just be 3, pretty sure, but we can prove it to ourselves. Negative log of 1 e to the minus third. Sure enough, 3. And how many sig figs do we want? Well, this has how many sig figs? Well, that has 2, so that means this would be 3.00. So that's your pOH. And then your pH, remember that's your pH plus your pOH equals 14. So if we subtract that from 14, we get our pH. So we say 14 minus 3.00, so we get 11.00 is your pH. All right, so this tells us that our solution here is basic, okay, because we're above 7 for our pH and below 7 for our pOH. All right, so do lots of practice problems. It can be kind of tricky running yourself through that roadmap, and you know, it's probably been a while since you had to use logarithms and stuff like that, so you got to get used to those in order to really be gelling on all these acid-base pH, pOH problems. So do lots of practice problems. Let me know if you have any questions, and I'll see you on the flip side.